Good morning.
Hi, you beat me to it. Good morning. I'm clicking around trying to adjust my screens. Good morning, everyone. Hi, Saja. I see you in the chat. Good morning to all of you. Hi, Alexandra. I hope you had an okay weekend and had a chance to review the chapters and yeah, and also, maybe get some rest or do something fun. I don't know, watch some football or something else. I don't know what else is out there to watch right now. Good morning to everyone else. Hi, Nathan. Hello, Owen and Gary and Patricia. Good morning. Sanjita, Isla. Good morning. Hi, Robin. And good morning, Luis. Hello, Keon. Hi, Daniel. Good morning. I'm glad you're all awake and ready to go. Yeah. Good morning, Andrea. Well, I'm going to just update the time on the exam, and I think we might even get started like a minute or two early. Um, if the things let me log in, we'll see. I had a complete shutdown of my internet over the weekend, so I'm hoping that'll help any internet issues. It actually got a little worse last
Could I
week.
could I ask
Yeah.
like a brief question about springs?
Sure.
Like when is the K negative and when is it not? Because I some of the formula says it's negative. The text inside, like just before that, says that it's positive, and then in the example it has it as positive.
K, the actual value of the K is positive. The equation is negative.
Okay.
Yeah. But the K value is a number that is like a ratio for the material. So it's an actual number. And it'll always be positive. But the equation itself has a negative because of that opposing direction. Um,
So like if that direction is like so if it's like pulling downward with if the object is like pulling downward with gravity, then the spring is actually positive. Then the formula is positive because it's going upward, right?
yeah.
Okay.
Yeah.
Okay.
That's correct.
Professor,
Yeah. Uh huh.
I finished the um, problem sets 8 and 9 last night, but I forgot to scan them before I went to bed. Would it still be possible for me to turn them in after the exam?
Yeah, that's always possible. And if you read the assignment, it'll say that in the assignment that anything late is fine to turn in.
Okay,
Um,
thank you.
yeah, yeah. The only thing that's not that I usually don't submit it late is the equation sheet. So make sure you guys get that in on time. Um, okay, okay. So let me update the time on the exam really quickly, and let me also remind you guys, as usual, um, okay, I think we'll get started at 10:05. Yeah. um, when you take an exam, make sure to practice academic integrity. Okay. The exam is meant to tell you how you're doing on a subject. It's not meant to change your grade. That'll ultimately, it can be the result, but that's always something you can change. So make sure to practice academic integrity from here on out on everything that you do. The moment that you decide to cheat or be dishonest on an exam, not just in this class but in anything that you do, is truly the moment that you give up your spot and you give it to, oh no, you give it to someone else. um, yeah, I hear people saying my connection is bad. Oh no. um, oh hell. Yeah, can you guys hear me okay? Some of you, most of you?
Yeah.
You
You're
can, so
just
just
cutting
cutting in and out.
a little bit. We can hear you mostly, but seeing you is a little touchy.
Okay, well, I'll try to. Okay, it's a little laggy. Okay, yeah, the internet's been off for me, so I'll try to make some. Um, if I'll put what I'm trying to tell you guys in the chat too. Practice academic integrity. Do not cheat. Oh, I see the sign on my end now. Yeah, I see it. I'm sorry, guys. um, the second thing for the exam is take a moment to go through the exam. Go through the exam and just make sure that you have a vision of how to complete all the questions so that you don't run out of time. Okay. Yeah, I'm gonna turn off my video because that's a good suggestion, David. Thank you. I hate teaching this way, but I'll make some changes in just a few minutes. So I'm gonna upload the exam. So again, 2 reminders: don't cheat. It's not good for you. It's a waste of time. And two, scan the exam before you start. Make sure you have enough time so you can submit on time. Okay, I'm gonna start the exam and I'll put everything that I said in the chat and I will give my reminders through the chat also. Um, okay, so the exam, I'm gonna give you guys like 3 or 4 extra minutes. The exam will be due at 11:10. I'm still here. It'll be due at 11:10 a.m. and it should be available now. Refresh your screen.
It is.
Okay, great. Hi, everyone. You have about 30 minutes or so left to finish the exam. Hi, everyone. You have just over 15 minutes left. The exam is due at 11:10. We'll start lecture at 11:30.
Oh, professor. I submit the exam and I send it to you in post way to make sure like everything is okay.
I got it through the email. I responded.
Okay. Oh, thank you.
Hi, everyone. You have about 5 minutes to submit. So continue doing whatever you need to submit. I'll be here in the chat if you need anything. And our class will start again at 11:30. So take your break. Hi everyone. So it's 11:10 right now. I hope you're finishing it off and hitting that submit button and that it's uploading and internet is on your side today. If not, continue trying to upload. I'll stay here for a few minutes in the chat. And then I'm also going to take a break and I'll see everyone at 11:30. We'll start again.
I submitted it several times. Is that okay? Just to like, I did what I could and then did more if I had a little extra time.
Hi everyone, I'm back. I hope you're all here too. Hello, hi Saja, hi Kian, hi Mehmet, hello. Um, I moved, hi Gary, hi Robin. I moved my desk around, so if you still hear me coming in and out, let me know. I'm gonna have to, I guess I just need to find a better spot. um, the good thing is I have wheels on my desk. I actually just installed them this weekend when I was trying to fix everything. So we'll see. Anyway, so welcome back. This week is all angular motion, chapter 10 and 11. And if you refresh your Canvas page, you'll see all the assignments and everything there. This week is only 2 chapters. So remember last week I said that week 3 was the toughest. And so now we're going kind of back on that down slope of some kind of normalcy. No day off, but at least it's 2 chapters over 4 days. So I'm going to, yeah, Henry, I totally agree. Week 3 was tough. Even same, I mean, yeah, everything you guys feel like I kind of get a gauge for it because I feel it in I feel it too, right? Yeah. So when last week was week 3, so it was tough. Yes, agreed, Amir. Yes. And then add in all the internet issues, and I'm behind. So if you feel behind, it's yeah. Take the rest of today to catch up. You know, we still have the 2 labs are due tonight. So several of you have already submitted, you know, great work for doing that. And if you haven't, you're still on time. So take the time to do it. Any comments, concerns, anything? Yes, and hopefully we don't have any, you know, out of the ordinary, unnecessary events throwing us off this week too. I agree. Well, rain, right?
I think 2 was worse than 3. Like last week, I thought that was easy. I had no problems with the homeworks, like very little, like minimal, nothing I couldn't just figure out, you know.
Yeah.
Even the equation sheet was a lot shorter because there was less topics, I feel.
Mhm. Yeah, and Owen brings up the point I was going to make too, that week 2 is when we start getting deep into physics beyond what we kind of intuitively know. So yeah, week 2 is thrown at you. So yeah. Well, I think these next 2 should be okay. Some of my favorite topics are coming up. So that's very, I love this section so much. But any general comments, questions, concerns from anyone?
This test kind of had a lot of writing on it. It was hard. It was harder to finish on time. Like it just
Yeah.
had so much writing to do. I hope you prepare yourself to read that test because it
Yeah.
is really sloppy.
I'm glad you guys feel that way because that was the point. Yeah, that was also why in the beginning I told you to make sure to read through the test first because you
Yeah.
did have an extra question. There were some easy ones, um, but some just take a little bit more time, you know, and it takes some more time to think. So, yeah. And I have a question. When do I think exam 2 will be posted? Um, I understand you guys are super anxious. That's what the chat says to me, and you don't mean to rush. Yeah, I'm working on it, and I anticipate that they'll be posted between today and tomorrow. I got through most of the grades, and then I try to leave I try to leave the exams for when I'm in a super positive mood. So when I had all of my internet, and I leave my grading
We
for
appreciate that.
yeah, yeah, me too, because it throws me for a loop too, and I don't, yeah. Um, so I leave my grading for the weekend. It's the only time I can do it, and yeah, I had internet issues this weekend too. You guys saw this morning, so I think I can catch up between today and tomorrow for exam 2 and 3. But my main goal is to give you guys a really good idea of what your grade is before the 30th or by the 30th. The 30th is the drop date for this class. So if you, yeah, if there, comes a point where you're considering dropping, I think you should talk to me about it. And then I will certainly work with you to do what's best for you. But by the 30th is the drop deadline for this class.
As
Is
long as I
there-
get a C.
What? Say that again, Nate.
As long as I get a C, I'm fine.
Nate, a C, a well-earned C is something to be very proud of. So, yeah, I'm with you. I'm with you.
Like a STEM class like this, a C is an achievement in my mind.
Yeah, I felt that way. I felt that way as an undergrad too, especially when I knew that I studied, I tried my best, and sometimes it works out and sometimes it doesn't, and you make changes. And it's okay. And Owen says it's another reason I like this one better. Seem to be more conceptual, more terms. Yeah, let me tell you guys, I love hearing your interpretation of physics. Those assignments to grade are my favorite. I read every detail. I love it. So any chance for you guys to explain physics in your own words, take it. So yeah. And Saja's right. C's do get degrees. Sometimes before you step out of your bubble, you don't realize that a C in a class is really good, depending on, what the circumstances were. My undergrad GPA at UCLA, my undergrad degree is in physics. And I thought my GPA was really bad, like really bad. My overall was something like a 3.1, 3.2. But my physics GPA was like barely a 3, like 2.95, something like that. And I was like, oh no, I'm not going to get into any grad school. Turns out the departmental average was a 2.7. So I wrote that in every essay. Every essay that I had, I wrote that I was above the departmental average, just so they would know. And Owen says, did you go to grad school at UCLA too? No, I went to, this might take us off a tangent, but I'll try to say it quick. I was really uncertain about what to do for grad school as far as what degree to do. And when I went to talk to my physics counselor at UCLA, she actually recommended that I didn't stay there. And she said that many students from physics UCLA wouldn't actually get into the physics program because they're looking for intellectual diversity. And she actually told me that was common for schools like Berkeley and Stanford too. So I did switch degrees, but my story is it's very intentful. Yeah, so I'll say that. But no, I'll just tell you guys super quickly. I got my master's in physics at Cal State LA, doing a bridge to doctorate program. So my master's was paid for, and that's kind of unheard of to have a master's unpaid for. Doctorate, yes, but master's, it's a little different. And then I went to UCR, and my PhD is in material science and engineering. So that's why I can teach engineering classes and physics classes. So it worked out. It really worked out. Yeah. So I can very much say C's get degrees. Yeah, you just got to paint that picture, right? Maybe next week I'll tell you guys much more of what happens. Yeah. You never know, but I promise if you just stay true to yourself, I will, Nate, next week. I have a Keon, you already heard this, but you'll hear it again, probably a different version of it. Yeah. Next week we'll have we'll do something.
I have a question about grades.
Yeah.
So is there a reason why our grades might have gone up if we during the test? Because when
I was grading one assignment during the test because I got up really early and I got things done, and so I didn't have anything to do during the exam. So I was like, well, let me get ahead and start grading. So I did I did one assignment that was easy to grade,
Did it have like bonus on it or something? Because I thought that like if you had all the points for like labs and homeworks, your grade couldn't go up unless you got you know what I mean? It could only go down if you missed a point, but it couldn't go up if you,
Yeah.
got another 100.
Yeah, that's a good math question. And when I add in another grade, that also increases the total of a grade. So if you had let's say a lower grade will count less the more assignments I grade.
But if it's all in that same, do you like separate the stuff into categories, like
Yeah,
labs?
it's all
So like if
Randy, it's all separated into categories, but I think I can look at yours afterwards and we can see what happened. Because if it's something out of the ordinary, I just probably made a mistake and I'll fix it.
I'm not complaining.
No, I know you're not complaining, but I think it's
Yeah.
specific to you. So, yeah,
Okay.
we'll
Sorry
we'll,
about that.
we'll check. Yeah, usually Canvas alerts me too, like, hey, someone's grade is really high.
It went up 0.06%.
Oh, yeah, that kind of makes sense, especially because of the categories. Okay, so I've talked enough. We have lots of time to talk this week and next week, and maybe in Physics 102, I hope too. Okay, I'm gonna start my slide set.
See you there.
I can't wait for you guys to meet Physics 101 from fall. That's the most fun to see the two classes get together.
Huh.
Yeah, it happens every year, and I'm here for it. I love it because, you know, in the other class, there's another Randy, there's another Keon, there's
Oh my
another,
God, there's a Randy? He's my age or is he like 80?
no, I don't even know who I'm talking about, but I'm saying there's people that you guys could really connect with in those classes.
Oh, not literally.
No.
Oh, okay. There's never a Randy my age.
Metaphorically.
Yeah, there could never be another Randy King or Randy.
And a few ways, that's for sure.
Okay, I've adjusted my windows so I can see the chat and I can see all of your boxes and reactions.
Couldn't handle another one. That's probably why.
You'd be surprised. You'd be surprised. Okay, so yeah, everyone, you're all super unique. So guys, we are going to go through chapter 10 and chapter 11 this week. And I know I get very excited over many topics in Physics 101, but hands down, chapter 10 and the idea of angular motion and torque is my favorite. So I can't wait till you guys see and make all the connections here. So up until now, we've pretty strictly studied linear motion, and we went a little bit into circular motion. And when we studied that circular motion, we were really looking at things that were moving in the path of a circle, right? And so that's fine. And now we're going to take all of our studies of linear position, velocity, acceleration, and force, and we're going to translate it all into angular motion. And so when you see this image here on the screen, you know, you're trying to loosen the bolts. We might, I don't know if we'll do harmonics just yet, Owen. I don't know. I don't think so, but I don't know. Yeah, so when you see the image on the screen, you're trying to loosen the bolts, right? And anyone who's ever done this, you know that right at the point of loosening the bolt, you really have to get it going, right? That forceful hit. And you can even, what is this thing called? This thing
Crowbar or a
crowbar?
a
Ratchet?
socket wrench? A socket wrench?
Maybe a socket wrench. The tire iron, I call that too. Yeah, okay.
A four-way? But it's
Yeah.
not a four-way, it's the one-way.
The cross, right? The crossbar.
Yeah.
And we know how to work with this, right? Notice that the guy's arm here, his hand, one hand is really close to the bolt, but the other hand that's applying the most force on a wrench, the other, the leg wrench. The other hand is really far away down kind of the lever, down the arm of that wrench, right? That's where you're applying that force to get this rotation. When we try to loosen this bolt, you notice that now the bolt is moving, but But is the bolt changing its position as a whole object? As an entire object moving, it's not going to, yeah, Daniel's correct. It's not going to change its position. It doesn't accelerate through space. The bolt is still centered around that axis, right? Around this center point here. It's centered here. It's not actually moving some space, some distance or anything. So we see that something did actually rotate, and now we're going to see that the thing that caused this rotation is the force here that this person applies at the end of that lever. So what we're going to do is find a angular version to everything that we've studied. So many objects will exhibit both translational and rotational motion. This is rotational motion, but you can also have translational motion if this bolt were spinning and also changing its position in space. A frisbee, does a frisbee do that, right? It turns and also changes, yeah. So anytime we say translational, we mean linear, we mean tangential. These are the things that we've been working with, especially chapters 2 with the kinematic equations, chapter 5 with Newton's laws of motion, everything we've done so far. Rotational is now what we're going to define in this chapter. And our goal is going to be to focus on the rotational motion of an object as a whole, and that's what we're going to call a rigid object. So a rigid object is one that we can model as having some continuous mass and that moves as one. Yeah. And so our goal then will be to find rotational analogs for each of the linear components. We're going to find a rotational position, rotational velocity, rotational acceleration, rotational mass, force, and even a type of energy. So we're going to start with everything that we kind of knew before, and you're going to see that it all very nicely translates over to rotational. I probably shouldn't use the word translate because that's that XY movement. So let's start with the first thing that we learned in kinematics. In kinematics, we learned the position X or Y. Now we want to learn angular position. So we start with how do we define the position in terms of a circle, something that's moving in an angular position. And this might seem very elementary, but we really want to make sure that we are specific to the terms of a circle, right? So anytime you want to define a point in a circle, you usually start by defining the center point, and that's the origin. From the center point, you can make a line to any position that you want. We're used to going all the way to the outside here and calling that the radius. Or we've been using the displacement vector, right? And from this point here, or this position here, you can define a point P of anything in space. And what you want to do to define that point P is create some reference line. This reference line is pretty much what you guys know as the horizontal axis, right? You make a straight line through it, and that's kind of, you measure everything from the x-axis counterclockwise, your angle thetas. So that's what you've seen before. If we rotate this disk, the particle P is going to move now to this position. So from this reference line, we see that it's moved to some angle theta, and it still has maintained that distance r from the center. So now using r, theta, and s, we can come up with some relationships that you've seen before. I'm just going to remind you of them. First is that we can say the angle theta is the distance s over r, or what you've probably seen more in math is the distance s equals r theta. And you might remember this distance s, or you might not, because I usually don't, is the arc length. And the arc length here is this path that the particle covered, right? That distance there, that length there. So the particle moved by some angle theta going counterclockwise here, and still has this length r from the center, and it's moved along a path s. So anything we know about circles, we can pull into this discussion. If we want to go all the way around, what is this? What is this in terms of a distance? Anyone out there? What is this length or distance?
Circumference, 2
Yeah.
pi r.
Oh, okay, yeah. I hear it from so many of you. It's the circumference. So what I'm just going to show you now are just some helpful things that you might need to remember. But for this slide, all you need to know really is that S equals R theta, the angular position. But we normally speak in terms of theta when we're talking about angles. And so for a circumference, the whole way around is 2 pi r. If we speak in terms of angles, we know that's 360 degrees. And this leads us to our handy dandy conversion, that pi radians are equal to 180 degrees. In problem solving, you might use this as a ratio or a conversion. So it might be more useful to write it this way, 1 over another. And, normally whatever you're looking for ends up on top. So if you want radians, you put the radians on top. If you want degrees, then you flip this over and you write 180 degrees. And when we're solving for a problem, normally in angular motion, we're going to use the unit of radians. But sometimes the problem will ask you a more practical answer, like revolutions or angle, and then to solve for degree or for a revolution. One revolution is one trip all the way around. So one revolution, for example, is equal to 360 degrees. And that's a little easier to talk about. Like if I ask you to turn 3 revolutions, you would spin 3 times and move, I don't know how much that is, 1080 degrees, right? And that's easier than saying 1080. Okay, so we have angular position. Now, what if this position changes over time? We know what comes with that is speed, right? So now imagine again that you have your particle that started at some initial position here, right? Some initial time at point A there. And as we're moving some time interval to final time, a change in t here, we are going to sweep out some angle that is some change in the angle there. And so our definition for the angular displacement of some rigid object is defined as that final angle minus the initial angle. And so this would be your displacement angle. And this,
What is sweeps out? What does that mean? Like
the reason we say sweeps out is just because it's angular, but it means that it continues its motion and it maintains its R. It maintains that radius, so it sweeps out through.
Oh, like a door or something.
Yeah, like a door. This is the sweeps out direction. Yeah, just like a door. The door is such a good example of torque. I can't wait. But people don't think about it. Think about why the knob for the door, guys, is all the way on the outside of the door and not on the inside. Is there a sweeps in? Oh, a sweep in. Oh, Daniel, that's a yeah. I guess if you said maybe you could think of it as a negative, but typically, yeah, or clockwise. And it would probably be moving opposite. But Keon brings up a good point about the word clockwise. Usually in angular notation, we will speak in terms of clockwise or counterclockwise. So this direction here is counterclockwise, and this is what you will see, this notation, counterclockwise. That's very common. And a question, does the angular displacement formula work for both radians and degrees or only for radians? It works for both. It totally works for both. Our SI unit, or our unit that is the right appropriate unit to use, is radians, but again, the question will likely ask you for a more practical answer in degrees or revolutions. Yeah. Okay, you guys are bringing up a bunch of good points. Okay, so if we have some angular displacement that happens over some interval of time, then we define that as our average angular speed. And notice we bring in our omega again. Average angular speed is defined as that angular displacement over some time interval. And this is only one step away from going to instantaneous motion, right? If we wanted to look at instantaneous motion, we would minimize that time interval and limit the value of t as close to 0 as possible. And so the instantaneous angular speed omega would be the derivative of the displacement, d theta dt. And notice how this is very similar to what we've done before, right? So this is like saying velocity over dx dt, where this one is tangential. And this is just the word to distinguish it from angular, but it's the same thing we've been doing. This is the tangential speed, and this is the angular speed, right? Angular speed. Okay, so if we look now at our angular speed, Luis says, will this be in polar coordinates? No, not often. It is defined, I guess it is polar coordinates because it's defined in terms of the distance r, which is the point to the distance to the point, and the angle theta. But the answer is usually in radians. Yeah, mostly because we're not working with the math, but we're looking at how a physical object is moving and what makes sense there. Whoa, the sun is out, y'all. The sun is out. It's in my face. Okay. Well, I'm blinded here. Okay, so the next step of looking at angular speed is looking at how the angular speed changes, if it does change, if it doesn't remain constant. And we know where that leads us. That leads us to angular acceleration, right? So if an instantaneous angular speed of an object changes over some time interval, then the object will have some angular acceleration. If we know a large time interval, we can figure out the average angular acceleration like we did before. And now we're using alpha. And notice that we write average because our everyday language will be instantaneous. Bless you. And so, yeah, go away, son. I agree. So our average acceleration is that change of angular speed over that time interval. And here you'll see that our units are radians per second squared or per second squared. So for speed is radians per second, and for displacement it's radians. And then we can take this one step further into the instantaneous world that we want to be in. And again, we limit that time interval to as close to 0 as possible to represent that instantaneous moment. And so the instantaneous angular acceleration is the derivative of the angular speed. And so again, really nicely, all of this follows because the physics here is the same. Now, what you see is that the angular position, speed, and angular acceleration are all analogous to the translational position, speed, and acceleration. So theta is like x in the tangential translational world. Omega is like our velocity. Angular speed is like velocity, and angular acceleration is similar to the tangential acceleration. Now, you're going to see that like we saw in the tangential or translational movement, that these are vectors. So they need to have some sort of direction. And what we're going to see with speed, and this brings us to our like clockwise and counterclockwise motion, is that a third direction is going to appear here. So I'm going to show you what it physically looks like. And then I think tomorrow we'll show you what it mathematically looks like. So this is the direction of angular vectors. So let's say, for example, in this situation here, we are moving, what is this? Counterclockwise. We are moving counterclockwise. So to determine the direction here, just in an easy way without any math yet, you can pretend that you are rotating your fingers, your 4 fingers using your right hand, your 4 fingers in the direction. So if you rotate your hand counterclockwise, your thumb will point up. Rotate your fingers counterclockwise and your thumb naturally points up. right? That is the direction of the angular speed for this particle. Now imagine if we were to do what Daniel said, sweep in or move clockwise. The same hand to move clockwise, my thumb now points down. So it shows us opposite direction of the particle speed that it's moving. So you can pretend as though that center axis that you're rotating about is a long pole, and it really is. We'll see that mathematically it's almost like a z-axis, right? Or in the k-hat direction, if this were like an x and this had a y here, or in any axis you choose, any way you want to rotate this. The point is you'll see a directional change here. So the direction of the angular speed for this particle will be out of the screen if it's rotating, if we move our fingers along this sweeping arrow that we see here, right? We sweep counterclockwise, you should see the thumb pointing right at you. And that's out of the screen here. And then if you try to flip your hand the other way and go clockwise, now the thumb is pointing into the screen. So that'll help us with direction, but we're going to come up with a mathematical technique to do this too. And it'll all make sense. So the next thing is that we can pull all of the definitions we just came up with, and because the laws of physics are the same here, you'll see that each one of them will help us derive our kinematic equations in angular motion, and they're exactly the same. So you'll see for the first equation here, this is like equation 2.13 that we learned in chapter 2, and now it has its angular components, and there are the rest of the 4. All of the components are exactly the same, but in our angular world. So all you've done is substitute x for theta, right? Velocity for angular speed, and acceleration for angular acceleration. And everything works the same here. So when we problem solve, we're going to problem solve the exact same way, but now this is specific to angular motion. But the relationships are the same, which, you know, tells us about this like grander unification of physics everywhere. Everything everything can be explained with the same laws of motion and the kinematic equations. Okay, I think we're ready to start a problem. Let's go. Okay, let's try it. A wheel rotates with a constant angular acceleration of 3.5 radians per second squared. If the angular speed of the wheel is 2 radians per second at t initial equals 0, through what angular displacement does the wheel rotate in 2 seconds? So first, let's just pull out all of the information that we have here, right? We have an angular acceleration. So this is our alpha. We have an angular speed at t initial. So this is initial angular speed. And they want us to figure out what is the angular displacement, so delta theta, in 2 seconds. T equals 2 seconds. So looking at having the acceleration, the initial speed and the time, this might jump at you right away, which equation to use from your kinematic equations.
Theta I plus v plus the velocity plus acceleration times time.
Yes, I think you're saying the big kahuna, which is what Henry is saying too. I think it's this one. Is this what you were saying? I hope.
Yeah, I think. Well, maybe not. I was trying to say it. I used like half of both ways.
Oh my gosh, I'm mixing up my.
That's what I was doing.
It's rubbing off. Okay, let me write this the right way. But I think you guys get it, that this is very much the big kahuna equation. When I was looking at the equations, I found another way of remembering kind of which one to use. And it really comes down to this initial velocity, which I hadn't recognized before. But this initial velocity and not having the final velocity is a real clue to use this equation. So yeah, anyway, so this is our equation that we would use because we have the time, we have acceleration, we have time, we have initial velocity, and we're solving for this displacement here. So let's plug everything in, all of our numbers, just like you would for a regular kinematics problem. Your initial velocity is in radians per second and time is in seconds. So notice that this cancels out the seconds. And then we have radians per second squared and seconds squared. So this cancels out and we're left with radians, which is the right unit for displacement. So the answer here is 11 radians, and this is correct. This is the way you would write your answer. Sometimes they're going to ask you for more information, and here they just went ahead and put it in degrees, and it's because of the second question, but you wouldn't have to. You could stop right here, and that would be correct. Now, if we wanted to put this into degrees, we would take the 11 radians and multiply it times our conversion and cross out those radians, and you're left with the degrees here. And so let me just make sure you see that this is just the ratio that we came up with in the first few slides. That's a 0. Right? And then you get your answer here. And so radians cancels out radians, and we have degrees. So we have 630 degrees, which I think for many of us, we could picture what that is, right? Radians, not so much. Yeah. Oh, Owen says, will you tell us what units you want? Yeah, usually the problem will tell you. If it doesn't make a clear distinction, your go-to is always radians. Okay. Now, this is what it's going to look like when they ask you for something specific. This is the next question. Through how many revolutions has the wheel turned during this time interval? So if you had radians here, if you had radians originally, and you wanted to go to revolutions, you would have to change to degrees, because we know one revolution is 360 degrees, and then go to revolutions. So that's why they showed it on the last problem. So remember, we came up with that conversion. One revolution is 360 degrees. So you write the ratio the way that you need to. The degrees cancel out. And now this is even more specific to something that we can interpret visually, right? We know what 1.75 revolutions is. Okay, so Randy, here comes your moment. Here's the next question. What is the angular speed, right? So now they want angular final for this final time. So remember that we already have the initial time and we already have acceleration. That's an alpha, or the Jesus fish. So now you can go to that kinematic equation that's not often used, but it's it's valid. And so here it is. I think this is the first one you were maybe mentioning, Randy, I think.
So I was mentioning this kind of, but like I was still putting in the initial velocity, and I just didn't do the 1/2 and the 1/2 part of the end.
Yeah, I got it. So here we use this and we have everything we need, right? We have all the values that they gave us. And again, we can just check the units. This should be in radians per second. So we have radians per second squared. This squared cancels out with the second. Is that right? Yeah. So we're left with radians per second plus radians per second. And our whole answer is 9 radians per second. So notice they don't give you a unit or anything to look for here. So your go-to is radians, unless they specifically ask for something. Yeah, something at least more telling. Now let's take a trip back in time and see if we can answer this question. Let's go back to chapter 2. Suppose a particle moves along a straight line. Oh, good. Tangential with a constant acceleration of 3.5 meters per second squared. If the velocity of the particle is 2 meters per second at an initial time of t equals 0, through what displacement does the particle move in 2 seconds? And then what is the particle's velocity at those 2 seconds? So You might recognize that this is exactly what we just did. We had these exact same variables, but they were exact numbers, and they were in our angular motion. So with the same idea here, you could solve this exact same problem, again using our big kahuna equation. And notice that the answer here is 11 meters. We had 11 radians before. And then the next solution is the same equation, and we still get 9 meters per second here. So exactly kind of one-to-one relationship. They're direct here, which is really nice. And similar to what we did before, we had our linear components and our angular components, and we want to be able to walk between the two, right? We want to be able to convert from one to the other. So we can look at angular motion and try to describe it in its tangential terms and then find a relationship there. So we did this before too in chapter 5, so I hope it's a little bit familiar. So imagine that this particle P then is moving in a circle, and it has some translational velocity vector V, and this translational vector V is always tangent to the circle. So here is our blob. You can imagine a chicken nugget, a potato chip, something like that that's rotating around this axis, centered at O. And this particle P right now, it's at some displacement, some angle theta, and it's some distance r away from that center. It's moving along the circular path here, and it has a tangential velocity or an L-fear, yeah. Wow, because of this pointiness, huh? So this particle will always have its tangential component, this angular, this velocity that's moving tangent to the path of the circle. And this is the equation we had before. Now the position and its path that it's moving along is s. Remember, this is just like dx dt, but we are using s because s represents the distance along this path. So the velocity is just like before, the change in position over time. But this s, we can also translate to the arc length, right? So if we bring back that definition of s equals r theta, and we now bring that into the derivative, the velocity becomes, this velocity becomes d of dt of r theta. Now, as you look at the particle moving, the distance r remains constant because it's on a circle, and that radius will remain constant throughout that circular path. So we move that r to the outside, and so we have that v is equal to r d theta dt. But we came up with a definition for d theta dt, and that was omega. So you guys remember this? V equals r omega. This is another way to formulate this, just like we did in the beginning, towards the end of chapter 5, actually. So this tells us what is the tangential speed in terms of the angular speed, the linear speed in terms of the angular speed. And again, the factor here is that distance r that it's rotating. So we can do the same for acceleration. Remember, we have tangential acceleration versus centripetal acceleration. And so here it is. We start with tangential acceleration, the derivative of the velocity over time. And we just came up with a definition for the velocity here in terms of angular components. So this is going to help us get to the angular components of the tangential acceleration. So we plug this in, d of dt of r omega. The r remains constant over the path, so we pull this out. And so the tangential acceleration is r d omega over dt. And just like we did before, we have a definition for d omega dt. And so that is the angular acceleration. So the definition of the tangential acceleration is the radius times the angular acceleration. So this helps us move back and forth between the two. And then I think we remember too that our centripetal acceleration is v squared over r, and now we have this definition for v is r omega, so we can put that in here. This will become r squared omega squared. One of the r's cancels out, and so you get r omega squared. And so we have our two definitions for acceleration, and together they'll give you the total acceleration of how this particle is moving, which is this the purple vector here. But that purple vector can be broken down into its two components. And then just to finish this off, we know how then to get the magnitude of this if we wanted to. The magnitude of the total acceleration is the sum of the squares, the square root of the sum of the squares of the two components. So tangential plus the radial or centripetal. And so we square these, right? Tangential is r alpha, so r squared alpha squared. And the centripetal here is r omega squared. So these two each get squared. You can pull the r squared out of the square root and you'll have r square root alpha squared plus omega to the fourth. And so here we have kind of complete definitions of how to really describe motion in an angular setting. How to describe motion in an angular setting. All of this is the same as what we did in chapter 2 and chapter 5 to describe motion in the linear world. So we have about 15 minutes. Let's try some conceptual questions. I love these. Okay. Ethan and Rebecca are riding on a merry-go-round. Ethan rides on a horse at the outer rim of the circular platform, twice as far from the center of the circular platform as Rebecca, who rides on an inner horse. When the merry-go-round is rotating at a constant angular speed, what is Ethan's angular speed? Now, before you answer this, you want to take a moment because we're in a different section. So this is not as intuitive as it may seem. You want to start with first realizing that they are asking for angular speed. Angular speed is omega is equal to theta over t.
They both have the same?
Yeah, so Randy, you got there, but I'm going to continue showing it because if you are looking for angular speed, you will see that there is no radius here to consider, right? So let us draw this out. I'll draw it out just to show you guys how I would prove this, right? So you have a merry-go-round, a very symmetrically perfect merry-go-round. And let me just tell you guys, a merry-go-round or any disc that's moving with its object on there is what we call a rigid object. A rigid object that has a continuous, you model the mass to be continuous throughout the entire object and it moves as one. So everything on top of a merry-go-round is kind of moving together. Okay, so Ethan is out here and he is twice as far. So we can call his radius just radius of Ethan. And then I think Rebecca is out here somewhere halfway and that's her radius. But R of Ethan is equal to twice that of Rebecca's. So that's how I'm gonna write it out. But either way, if we look for angular speed, there is no radius that will come into play when we're looking at angular speed on itself. So just like Randy tells us here, our answer should be the same as Rebecca's. When the merry-go-round is rotating at a constant angular speed, what is Ethan's angular speed? It's going to be the same. Okay.
Will the arc that the one on the outside covers be larger than the arc of the one on the inside?
I think so.
Okay.
Yeah. Okay, let's try, we got it. Let's try this one. Same situation. When the merry-go-round is rotating at a constant speed, constant angular speed, describe Ethan's tangential speed. So we're working in an angular world. So you want to write tangential speed, and I'll show you guys tangential speed in terms of angular components. And so now when you write out this velocity in terms of Ethan or in terms of Rebecca, you'll see that one is twice that, right? So now you can see what happens to the velocity here. Um, yeah, something's going to be faster. So a comment from Owen. I guess it makes sense because if they're both at the same position but just further out, they still revolve at the same rate. That's exactly it. But you really want to think about, when does that tangential speed come in? Because we also know that, imagine if you're in like a marching band, right? And the whole marching band
Oh,
is turning the corner, right? If you're on the inside of the corner, you're kind of just standing in place. But if you're
twisting.
on the outside of the band, you're practically galloping like a horse trying to keep up, right? The rest of your crew is just following you all the way around while you're centered in place. So there's a difference between angular speed and tangential speed. Um, so here, yeah, it's not like one will cut ahead of the other. That's correct when we describe the angular speed. But when we describe the tangential speed, which is that point tangent, right? We're going to see that a little bit different. Um, yeah, yeah. So here, yeah, you're going to see the answer to, it should be twice Rebecca's. And the way to calculate this is doing it this way. You'll see velocity of Ethan will equal just, his radius or whatever that is, omega. And then when you put in that he's twice as far, should this be 1/2?
Hmm.
2r equals Ethan. No, that's right. 2r equals Ethan.
Well, so no, Ethan is 2 times the radius is Rebecca.
Yeah, that's correct. That's correct. And so when we multiply this out, you'll see that Ethan will be moving twice as fast, or that Ethan's tangential speed will be twice as fast. So our answer should be twice as Rebecca's. Yeah, it will be. And then Henry asks, can you explain radial acceleration? I understand tangential acceleration. Yeah. I'm just going to take us back to our image. So the radial acceleration is the one that pulls us and keeps us gravitating towards that center axis. A good way again to imagine it is like the yo-yo on the string. If you're like spinning the yo-yo or anything that you are flinging around, there's something that's keeping you, a centripetal acceleration that's keeping you in. If there wasn't a string or something keeping you in this center, pivoting around this axis, you would fly straight out of that path, and that's your tangential. So radial acceleration is the same as centripetal, just has an opposite direction. Yeah. Okay. I hope we're okay there. And we got those questions. Let's see. We have a few minutes. Let's try a question. Yeah. Oh, yeah. Like, yeah, those are, yes, Randy, that's correct. Like the force of gravity and the normal force, they kind of balance each other out. Yeah, that's in a linear world, and absolutely. Okay, let's try this question. This one always, this one reminds me of like how old physics is sometimes when you try to pull in different objects from now. In a typical CD player, the constant speed of the surface at the point of the laser lens system is 1.3 meters per second. So when you're scanning a CD, there's an optical lens that's reading it, right? And that's where that laser pulls out is out. And so that's what they mean by the laser lens system. And where that laser is reading the CD, the speed is 1.3 meters per second. Notice that it says a constant speed of 1.3 meters per second, right? Okay, and then it says find the angular speed of the disk in revolutions per minute when information is being read from the innermost track of a radius of 23 millimeters and the outermost final track of a radius of 58 millimeters here. And so we can call one of these, like this could be the first track, this could be the last track. So one could be like an initial and the other one could be a final. But this problem is asking us two separate events, right? What is the angular speed initial? And then what is the angular speed final? And they give us the radius and they give us the velocity. So once you write all this out, V, omega, and you have R, you can see that we're just going to use our relationship of tangential speed to angular speed. But we're going to do it twice, once for initial and once for final. So here's the initial and here's our relationship. Remember, this comes from V equals R omega. And they told us a constant speed and a radius. So we solve for the initial. And here we have 1.3 meters per second over 23 millimeters. That's what that is. And notice the meters cancel out and we are left with radians per second. And they asked for the answer to be in revolutions per minute. Yeah, Nathan, you got the equation right. So we need to convert this to revolutions per minute. So first you can work on the radians and cancel that out with 1 revolution is 2 pi radians. That's a quick one, right? So we skip degrees altogether. That might be something nice to include in your equation sheet. Then we can work on the seconds and go from seconds to minutes. So this seconds down at the bottom here cancels out with this top seconds, 60 seconds per minute, and we're left with revolutions per minute. So we want to do the same thing for the final scenario. And here it is. 1.3 meters per second, that constant tangential speed. And the 58 millimeters, the last track on the CD. And we convert again here using this ratio, 1 revolutions over 2 pi radians and 60 seconds over 1 minute. And then you get 2.1 times 10 to the 2 revolutions per minute. So you've calculated for the initial angular speed and the final angular speed. So we have those two things now. There's more to the question, but we just, keep in mind that we did solve for that. So the next part, the maximum playing time of a standard music disc is 74 minutes and 33 seconds. How many revolutions does the disc make during that time? So again, just kind of make sure you understand all the time, that all the information you're given here. You're given a delta T. Yeah, Owen, what's that? They tried in one slide, they put a Blu-ray disc. And these slides aren't that old. It's like 2 years ago, 2018, 2019, like it's not that old. Yeah. I used to have zip discs. That was like a thick floppy disk. Okay. How many revolutions does the disk make during that time? Yeah, maybe we should just talk about everything in terms of memory, right? Who cares about the physical nature of it all? Yeah. Okay, so we have a delta time here, and they want to know how many revolutions. So how many times are we going to spin around? So to get to revolutions, you somehow need to know what is that change in displacement. What is that angular displacement that we're going to have? We will need to change the time, right? That's probably one of the first things you want to do. Change it all to seconds. So this should be in units of seconds. And then once you have time in seconds, you could use the initial angular speed and final angular speed and time to solve for this. Remember, we also have the initial angular speed and the final. So having these two and the time, we can easily get to this displacement here. Okay, so let's convert it all to seconds. 74 minutes times 60 seconds per minute plus the 33 seconds. This is our total time here. And remember, you could do this in several steps, but one of our kinematic equations gives us this one. You guys, this is one that we don't use very often. So if you didn't catch it right away, that's okay. But remember, we have time, we have this final angular speed, we have the initial angular speed, and we are looking for this change in displacement. So this is one of our kinematic equations. It's actually the first one we came up with. We don't use it too often because, we're ahead of that, right? Oh, it's 12:30 on the dot. So let me solve this. Yeah, it's kind of basic. I agree. Okay, so we plug in what we solved for on the last two slides, the initial and final angular speeds, the time that's given to us. Notice that these 2 seconds will cross out with this second, and very nicely we're left in our units that we want. So that's the radians, but I think they asked us for revolutions. And so now we have plenty of ways to convert quickly to revolutions. So radians cancels radians, and we're left with revolutions. So 2.8 times 10 to the 4. There's
Could,
one part. Uh-huh.
Could you, I don't understand the WI and the WF. Where does that come, the omega?
We
Omega,
solved,
I don't understand that.
we solved for these originally on the last slide. So they came here. This is the initial and final that we solved for. And then the equation that we use might not look familiar, but it's this first one right here. Oh, not the first one, the second one right here. Yeah, so it's only a matter of keeping track of everything you've done and that you have available to you. So we use this. I know, right? It doesn't. It seems like, where did all this come from? But we've seen it. Okay, I'm going to leave you guys here, and tomorrow we'll finish off this problem. This is the last question that it's going to ask. Then what is the angular acceleration? And then we are right on schedule to continue with our discussion of torque tomorrow, and to start our lab. So yeah. Oh, and Daniel says, is this PowerPoint on Canvas? It looks like the one on Canvas doesn't have the example slides filled in like this one. Daniel, that is correct throughout the entire semester. I normally don't put the examples, the answers in there, but I'll put them in the at the end of the week in the resources. But these examples are exactly like the ones in your textbook. So if you're looking for the actual info, it's all in your textbook too. Yeah, like exactly. It's pretty nice. Okay, so I'm gonna stop here, and I'll stay on for a few minutes today. I do have to go help my mom at 1 o'clock, but I will stay in case anyone has any questions. And for those of you who couldn't stay with us throughout the lecture, I really appreciate it when you let me know. You know, just that you can't be here. And of course, as all of you know, the lecture is available for watching anytime you want. So again, I'm going to stay on, but I am going to stop recording. You guys are totally free and good to go, but I'm going to stay. I'll be here.